Hi learners, today we are going to discuss polar plots which have a very significant role to play in the plotting of the Nyquist curve. What are polar plots? Transfer function gj omega can be written as magnitude of gj omega, angle of gj omega. So both magnitude and phase, they are the function of frequency. As omega is varied from 0 to infinity and m and phase are plotted as a phasor, then the locus of the tip of the phasor with frequency is called the polar plot. So it means what? That a polar plot contains complete frequency response characteristics in a single plot. It can be used to ascertain closed loop stability using open loop transfer function. So polar plot is what? It is the plot of magnitude of the sinusoidal transfer function versus the phase angle. It is obtained as omega is varied from 0 to infinity. And positive phase angle is measured counterclockwise from the positive real axis. The polar plot is often termed as Nyquist plot. What are the various steps to draw the polar plots? First of all, we write down the transfer function of the system in S domain. Then put S equal to j omega and get expression for the magnitude of the transfer function and angle of the transfer function. Then we'll check whether the polar plot intersects with the real axis by making the imaginary term of gj omega hj omega equal to 0 and find the value of omega. Similarly, the point of intersection of the polar plot with the imaginary axis is obtained by making real term of gj omega hj omega equal to 0 and finding the value of omega. Then for omega equal to 0, omega equal to infinity, and a few intermediate frequencies like we have the frequencies that we have determined in step 3 and 4, will calculate both magnitude and phase angle and will complete the polar plot. The overall procedure will become clear with the help of an example. Here we have considered a simple RC network. The transfer function for such a system, it is given as gj omega. This is equal to 1 divided by 1 plus j omega t. If we separate its magnitude and phase angle, so its magnitude will be given by 1 divided by root of 1 plus omega square t square, and its phase angle will be given by angle minus tan inverse omega t. So these are the, we are following this step. First of all, we have substituted s equal to j omega in the transfer function. Then we have obtained the expression for gj omega and phase of gj omega. So magnitude of gj omega and phase of gj omega. Then at omega equal to 0 and omega equal to infinity and some intermediate frequency, we'll determine the value of the magnitude and the phase angle. When omega equal to 0, m will be equal to 1. When omega equal to 1 by t, m will be equal to 1 by root of 2. When omega equal to infinity, m will be equal to 0. Then about the phase angle, at omega equal to 0, phase angle will be equal to 0. This is tan inverse 0. At omega equal to 1 by t, phase angle will be equal to minus tan inverse 1. So this will be 45 degree. When omega is infinity, phi will be equal to minus 90 degree. Then we'll draw the phasor plot. So at omega equal to 0, here it is omega equal to 0. And here we have to take up a phasor that is having a magnitude equal to 1 and phase equal to 0. So this is a phasor that is having a magnitude equal to 1 and phase equal to 0. At omega equal to 1 by t, magnitude is equal to 1 by root of 2 and phase is equal to 45 degrees. So we are taking a phase equal to 45 degree. So positive phase is taken in the clockwise direction. So this is 45 degree and it is having a magnitude equal to 1 by root of 2. And when omega equal to infinity, m is equal to 0, phi is equal to minus 90 degrees. So this is this point. So we have got 3 points on the, this is this point. So the polar plot, we'll just join the tip of this. This is first phasor, this is second phasor, and the third is simply a point. When we join the tip of these phasors, we'll get the polar plot, that is a semicircle that is represented like this. So at this point, omega equal to 0, at this point, omega equal to infinity, and at this point, omega is equal to 1 by t. Similarly, this was a very simple polar plot, and it's not having any intersection with the real or the imaginary axis, so it was very easy to plot. Then we take up certain transfer function that is slightly complex. So it is having two poles at s equal to -1 by t1 and s equal to -1 by t2. So first of all, we are having the transfer function gs, for which we want to draw the polar plot. The first step is, first of all, we'll substitute s equal to gj omega, then we'll separate the magnitude portion and the phase portion. Magnitude portion will be equal to root of 1 plus omega square t1 square. Then corresponding to this magnitude will be 1 plus omega square t2 square. K is simply the constant. So angle of gg omega, K will not contribute any angle. This term will contribute an angle of minus tan inverse omega t1. This will also contribute an angle of minus tan inverse omega t2. So that is represented like this. So first two steps we have completed. We have substituted s is equal to j omega. Then we have calculated the magnitude portion and the phase portion. Now we'll get the value of gj omega at various frequencies at omega equal to 0 and omega equal to infinity, and wherever it is wherever this gj omega, it is cutting the real axis and the imaginary axis. In order to get the point of intersection of gj omega with the imaginary axis, we'll put the real part of, we have just manipulated this gj omega in two parts. First is the real part, this is the imaginary part. In order to take up its intersection with the imaginary axis, we'll just put up the real part as equal to 0. So when we put the real part equal to 0, we get the value of omega is equal to root of t1, t2. So this is the frequency at which polar plot cuts the imaginary axis. Then putting imaginary part equal to 0, we get the value at which the polar plot cuts the negative imaginary axis, so that and that we'll get like this. No, when we put the imaginary part equal to 0, then we'll get the value at which the plot cuts the not negative imaginary axis. It will, where it cuts the real axis. So that also will get. So this is equal to k root of t1 t2 divided by t1 plus t2. So the resultant polar plot is obtained by obtaining the value of magnitude and phase at omega equal to 0, at omega equal to infinity, and at omega equal to 1 by root of t1 t2. And if we put the imaginary part as equal to 0, then we will get omega will be equal to 0 only. So it is not cutting the, I mean, we'll just reach at this point only. So we are getting to 1 point only. This is not the thing that, please do not consider this equation. When we put the real part as equal to 0, then omega will come out to be root of t1 t2. This is the frequency at which polar plot is cutting the imaginary axis. When we put this portion as equal to 0, then we'll get omega as equal to 0. So omega equal to 0 is the frequency where the polar plot is cutting the real axis. So we'll get 3 point. This is at omega equal to 0, at omega equal to infinity. Then at this point, this we have calculated within this. This is omega is equal to root of t1 t2. So we get 3 point. We just make up a curve passing through these points, and we'll get the polar plot of this particular function, this function that is having two poles at -1 by t1 and -1 by t2. This is basically giving you the value of the magnitude of the gj omega at omega is equal to root of t1 t2. So this is A. This is point A. So A is equal to k root of t1 t2 divided by t1 plus t2. So here we have got the magnitude, angle is -90 degree. Here magnitude is equal to k, angle is equal to 0. And then here magnitude is equal to 0, angle is equal to minus 180 degrees. So at 3 value of the frequencies, at omega equal to 0, omega is equal to 1 by root of T1, T2, and omega equal to infinity. We get the value of the magnitude, we get the value of the phase, then we just draw the phases and then we join their tip together to draw the polar plot, and polar plot is taking this shape. Within this figure, we have shown the polar plot of various simple transfer functions. So this is the polar plot of 1 by j omega. This is polar plot of 1 plus j omega t by j omega t. Then this is the polar plot of j omega. This is the polar plot of 1 plus j omega t. So likewise, we can see that we can easily draw the polar plot of any transfer function by following the simple steps that have been explained within this video. Thank you so much for your patience hearing. Within the next video, I'll be explaining the use of the polar plot in the Nyquist stability criteria so as to ascertain the stability of the system. Thank you so much.